Okay, thanks a lot. Right. So, welcome to the last session. There is a title in this talk: Can computer science help climate policy? And there was a discussion about multidisciplinary efforts, and Patrik Jansson, who also participated to the discussion, already mentioned this collaboration that we have been having for a number of years, perhaps more than one decade. And what I would like to do in this talk is to give you a little bit of an overview of what we have done. And we means a number of people, among others, Patrik and myself, but also Nuria Brede and Tim Richter from the University of Potsdam, and Cesar Ionesco, who perhaps initiated the whole collaboration, who is now teaching at the Technical University in Bavaria, in Deggendorf. Right. So in the previous talk, we have seen that policy making in matters of climate policy is difficult. And the previous speaker was mentioning a gap between climate science and climate policy. And I would like to put our work in the perspective of this gap and try to convince you that this gap is in fact quite big. There was another question popping up in the discussion on multidisciplinarity, and was what needs to be done at least to avoid a climate crisis. And I think that this picture makes quite clear what needs to be done. This is something that was published in 2018 in the summary to policymaker of the IPCC special reports on the impacts of global warming. And what you can see is that roughly and by large, if we want to stay within the 1.5 degrees target, or let's say the 2 degrees target, we need to decarbonize by more or less the middle of this century. So this diagram has on the horizontal axis time from 2010 to 2100, and on the vertical axis global emission. And you see that there is a kind of corridor. In fact, there are two corridors corresponding to different requirements. But the blue corridor is telling you that roughly starting at 2050 or perhaps 2060, we have to go to negative emissions. So what needs to be done is pretty much clear. The problem is, however, how to get there. So what I want to say is that considering the fact that this diagram has, or these results have not changed significantly in the last 5 years, we can say that it's quite non-controversial that climate science has provided enough evidence for the need for global negative emission. By 2050, 2060, it doesn't matter. But the problem is that we do not know how to achieve such low emissions in such a short time. And this is, of course, not a scientific question. It is fundamentally a political question. But the interesting thing is that it can be sliced down into a number of questions that can be tackled scientifically. And here there are some examples of this question. For instance, which climate decision over the next decades are likely to matter most? Or do fast green transformation lead to more or less inequality and migration? Or how do uncertainty affect optimal climate decision? And what does optimal mean when a decision had to be taken under conflicting goals? For instance, saving the climate on one hand, but on the other hand, keeping the economy running. And these are kind of questions that can be addressed with rigorous methods, and we think that computer science can contribute towards at least understanding and perhaps also answering some of these questions. And we have been doing some work in this direction. So this is the context of this collaboration and of the work that has been going on between Chalmers, Oxford and Potsdam University for a number of years. So I'm going to walk you through some results, more or less like 2 slides per paper, and then try some conclusions. I want to mention that some of these results have been obtained within TIPES, which is tipping points of the Earth system on Horizon 2020 project. And I'm going to show you some code or some code snippets. And this, of course, we do not have time to really dissect this code and try to understand it, but you can find the source code, which is a literate Idris file that I've used to generate these slides in this GitLab repository, and it should be publicly available under 2024 PROPL'. I would like to start first with Cesar Ionescu's formalization of vulnerability. This was a PhD thesis in 2008, but it was published more or less only in 2014. And this is a paper that I really would like to read if you are a computer scientist. First of all, because it's a lot of fun. And secondly, because it is probably the beginning of this enterprise that Patrik was talking about. This is about modeling vulnerability with functional programming and dependent types. And in those days, vulnerability was a big issue around 2005, 2010 in climate impact research. There were a lot of studies about the vulnerability of coastal areas, for instance, with respect to sea level rise, but also other kinds of vulnerability, for instance, of poor societies to extreme events and so on. And I think that there was this problem that many of these definitions, IPCC definition and studies, they were actually not really very consistent. And Cesar tried to put an umbrella around all these definitions and came up with this formulation, which says that vulnerability is a measure of possible harm. And it turned out to be a very simple and yet very powerful formalization. And perhaps the first thing that we could say is that according to this understanding, vulnerability being the composition of 3 functions is a function. It's not a number, it's not an index, it is not a point in a operational safe space, it is a function. So perhaps it's worth looking at what kind of function vulnerability is, and therefore we start with possible, and the idea of possible is that it is a function itself, of course, which takes values in some state that might be a climate state or a climate economic state. It can be modeled with an agent-based model, with an integrated assessment model, it doesn't matter. But starting from this initial state, it generates a functorial structure of evolutions which are predicated on that state. And the idea is that evolution X is the type of scenarios. For instance, it could be time series of values of type X. It could be just X itself. It could be a pair of states representing the initial state and the end state of a trajectory. And F is an uncertainty functor. It could be a list, it could be a finite probability distribution, something that models the fact that when we start in a given state, we have a set of possible evolutions and not only one evolution. And then, of course, harm has to be a function that takes an evolution on states and gives back some kind of value. And measure has to be a function that takes a functorial structure of values and delivers some other result. Perhaps W is in the most cases V itself. And then, of course, we know what is the type of vulnerability. And the question is, okay, what do we have learned about that? Well, one of the interesting things that can be learned from this formalization is that measures of vulnerability have to fulfill a very natural condition. If harm increases along a trajectory, if every point of a trajectory becomes a little bit worse, it shouldn't be the case that measures of harm decrease. And this can be formalized in a very simple way using dependent types. And one of the things that came out from this formalization was that, in fact, many, or a few very popular measures, for instance, um, the most likely evolution, actually do not fulfill this condition. So that means that we can partition vulnerability studies into two sets: those that are semantically consistent, and those that use vulnerability measures that do not fulfill this very basic requirement. So there were a few lessons learned from this formalization. And one was that formalization is, of course, closely related with generic programming, as we can see, for instance, from the declaration of these monotonicity conditions. We have a functor, we have two preorders, and so on. But of course, dependent types, okay, no surprise for us, are best for expressing generic program specification. But perhaps more interestingly is that this kind of specification are useful not only for testing or for proving the correctness of implementation, but also for understanding the semantical correctness of approaches, like, for instance, the usage of most likely measure instead of perhaps expected value measures. Let me come to the second series of publications, starting again with vulnerability modeling, the PhD thesis of Cesar Ionescos in 2008. I'm giving you an account which is came a little bit later in a paper about extensional equality preservation that was published in the Journal of Functional Programming in 2021. But the original ideas go back to the thesis of Cesar. I've mentioned the fact that evolution of X is the type of scenario. So the question is, what are computational principles that generate scenarios? Can we have some kind of can we describe some kind of computational engine for scenarios? Well, in a time discrete settings, which is most relevant setting in climate impact research or also in agent-based model, deterministic dynamical systems are just endofunctions. And so scenarios can be obtained by integrating or iterating a system. And so the flow of a system over n step is just, or the flow of f over n step is just f to the power n. So I've mentioned the fact that uncertainty can be represented functorially. So that means that if you start from a given x, you do not get just a unique next state, but you get perhaps a probability distribution or a list of possible next states. That's not a problem, because if this functor is also a monad, then we can integrate a monadic system in much the same way as we integrate a deterministic system. And this was a fundamental recognition, or something that was in a certain sense discovered when Cesar was working in his PhD thesis on these systems. Having monadic operation allows us to generate a flow in much the same way as we do for deterministic system. We just need to replace composition with Kleisli composition and the identity with it our return. So that means that we can compute evolutions by just integrating monadic dynamical systems, and scenario can be, of course, also full trajectories. And we can treat deterministic, non-deterministic, stochastic, fuzzy systems in a very consistent way, which is very important in order, for instance, to compare different models and different approaches, for instance, different integrated assessment models. At this point, we had like a consistent theory of the evolution of these systems, but we have no human intervention. And I've looked back when I was preparing this lecture, I've looked back in my notes, and I realized that we started thinking how to integrate human decisions around 2012. And then we came up with this Computational Theory of Policy Advice and Avoidability, also Journal of Functional Programming in 2017, so 5 years later. But you see here on the left that there is something like a sigma function that now does not just take an x into a monadic structure of x's, but in order to do so, it also takes as a second argument a feasible control, something that represents human decisions. And I do not have time to get you through this theory in any kind of detail, but let me say that the basic idea is that we have two sets of software components, one which is used to specify a decision problem over a finite number of decision steps, and one which can be used in order to solve that problem in a verified fashion. And this is an example for the specification components. You see some of the symbols that I already shown you in previous slides. We have a monad, we have an x, which is not now a type by a function from time steps to type. We have a set of controls, which depends on a particular state, and so on and so forth. Solution components are generic definition. For instance, policies are functions from states to controls. And the theory is applied in two steps. In a first step, one defines all the specification components. For instance, says what is M? Is a finite probability, is a climate economic state. And in a second step, one applies backwards induction and computes a sequence of policies, and then type checks that this sequence of policies fulfills a lemma that tells that for every time step and for every number of decisions n, the policy sequence obtained by applying backwards induction is indeed optimal. A further work or a refinement or an extension of this work is again about semantic correctness. And this was Nuria Brede, who was giving a major contribution to the question of under which condition it is legitimate to apply backward induction. And this is very important because integrated assessment models, and we've heard a little bit about them in the beginning of this workshop, for climate policy are based on sequential decision problems, and backwards induction is a methodology that computes policy sequences for sequential decision problems that maximize a so-called Bellman equation. But solving sequential decision problem means computing sequences that maximize a different function. And you can see, at least from these pictures or code, that these functions are not definitionally equal. And so the question is under which condition val and val prime are extensionally equal, and Nuria answered this question by coming up with three conditions which are sufficient for the equality between these two functions, and then discuss also counterexample. I'm more or less running out of time, so I do not have really time to discuss applications, but there have been at least two interesting applications to these theories and to this formalization to concrete problems in climate policy. One focus on the impacts of uncertainty on optimal emission policies, and the other one focus on finding out which climate decisions under uncertainty really matter most. Both on non-computer science journals. This is important for the conclusion, which is my last slide. I've tried to give you some account of a research program that we have been following over the last 10 years that is based on the conviction that principle of programming and type-driven analysis and dependency type formalization can help formulating, understanding, and sometimes answering crucial questions at the interface between climate science and climate policy, and thereby contributing filling this gap that I was mentioning at the beginning of my talk. Another conclusion is that, as I was saying, we've published in different kinds of journals, and publishing in computer science journals was challenging, but always very rewarding. And on the other hand, these last two publications that I was mentioning on natural science journals, they were very frustrating because of typesetting issues. It was not a problem of reviews or reviewers. It was just like that it is impossible nowadays to uh, print code on natural science journals. From the point the papers were accepted to the point in time in which they were published, it was sometimes 3 or more months because of problems in typesetting code. Uh, a fourth conclusion, which is perhaps a little bit negative, we have not been able to convince many climate scientists of the usefulness of thinking functionally. And there is an attempt at explaining why we have failed in a new paper. This is submitted again to the Journal of Functional Programming to avoid these typesetting problems. And it is available on arXiv, and perhaps you want to look a little bit at it. And from the last sentence of the abstract, you can see that we have not given up. So we still hope that what we are proposing makes mathematical physics more accessible to computer scientists and functional programming more palatable to modelers and physicists. And this is the end of my talk, and thanks a lot for your attention.
Thank you for that very interesting talk. Are there any questions?
If the state is partially observable, how can it be incorporated in the framework of formulation?
Yeah, that's a very interesting question. It depends a little bit on what you mean with partial observability. There are two possibilities. One possibility is that, of course, if you have a function, so if you have a function that goes from x to mx, then you can very easily create a function that goes from mx to mx. So partial observability would mean in that case that the initial value or whatever value is, you do not have exactly one point. You have a cloud of possible initial conditions. The other possibilities with partial observability is that you only know a few features of your system. This is something which is in a certain sense already incorporated in this framework. So if you think, for instance, of a general circulation model or even of an integrated assessment model, these are completely unusable for this kind of rigorous computation. You have somehow to aggregate those states in macroscopic, more simple states, because the cost of backwards induction, either over a number of time steps, let's say of 10 or 20, are otherwise unmanageable. So in a certain sense, you have to have done some work in advance before you can formulate uh, um, a sequential decision problem or an optimal decision problem in a useful way. You have, for instance, have to have tabulated very complicated states, and you have to have lookup functions that extract from this tabulated state only a kind of macroscopic observables, GDP value, something that decision maker, can see. Decision maker cannot see the whole state of the world in order to make a decision. They have to rely on very, very aggregated state. I hope that this answers your questions.
Yes, thank you.
Any other questions?
Thank you very much for the interesting talk, Nicola. Is perhaps what is there a bridge from the rich grammar of dimensions of mathematics to just really, really high performance? So in the previous talk we saw you can compile to GPUs and make things really fast. So is there some strategy to go from Idris to GPUs? So staging or some compilation strategy where you could execute this stuff at speed and scale as well?
Yeah, I think this is, I cannot really answer in a very different way. It's a very good question. Uh, we have an example of a slightly different application. This is about tokamak fusion reactors. And there, for instance, we have linked a very complicated model, which is called DREAM. Patrik can tell you a little bit more about that. It's a very sophisticated model for solving systems of partial differential equation with CPU times from minutes to days to very simple Haskell optimization codes. So it is possible to do that, but again, you have to use memoization, you have to use lookup tables, and you have to introduce some kind of interfaces. This was, again, it's the coupling problem in a certain sense. And the other thing that you can do is to simplify from the beginning the models. For instance, in this deepest project, our partners in Belgium have been developing a very small simulator, climate simulator. So this is something also that was discussed this morning, like 6 ordinary differential equations that are then calibrated in order to produce for certain problems and in on certain time scales, good approximation for, I don't know, melting rate of Greenland, sea level rise, and this kind of variables. This needs to be done.
Okay, thank you. Let's thank our speaker again.